Section P.3, Radicals and Rational Expressions. Now in this section, it's going to be very helpful to memorize or know a couple of lists, and I suggest when you take your exam that you write down these lists as soon as you get your exam packet out in the margins. That way you can use these lists in future problems, and we'll see that today as I do this lesson. The first lesson, or the first list, is the perfect squares list, and I'm assuming you know this list. If you don't, you can always come up with it using your calculator. Okay, so you start off with 1 squared, and that's equal to 1. 2 squared is equal to 4. 3 squared is equal to 9. 4 squared is equal to 16. 5 squared is equal to 25. 6 squared is equal to 44. 13 squared is 169. And this goes on forever. But those are ones I definitely want you to memorize or be able to come up with. The next list is the perfect cubes list. And we start off with 1 cubed, and that's just 1. 2 cubed, and that is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 2. Ooh, I just had a brain fart. Let me go on right. 5 to the third power is 125. 6 cubed is 216, and then etc. And I didn't write this down on the list, but if you have x squared, that's a perfect square. It comes from x squared. X to the fourth is 4th. X to the third squared is x to the 6th, and so on. So anything with an even exponent is automatically a perfect square. We'll look at that later. Okay, so if we have the square root of 64, that's the same thing as 8. If you look at this list here, you see that 8 squared is 64. This is true because 8 squared equals 64. Right there. Square root of 49 would be 7. And you can see that right here. Okay. Now the cube root of 8 would be 2, because 2 to the third power is 8. The cube root of negative 8 is going to be negative 2, because negative 2 to the third power equals negative 8. Negative 2 times negative 2 times negative 2. Oops. Got my negative sign there. Times negative 2 equals negative 8. Okay. So I'll be referring back to this list throughout this section, so hopefully you have it written down, and then you can even write on a separate sheet of paper so you can have it while you're doing your homework, or have this list out while you're doing your homework. Okay, evaluate 6. Okay, and again, if you go back to the list up here, you can see that right here. Okay. Now here I have negative square root 25. So this right here, the square root of 25 is just 5. And then you drop down your negative sign, so you have negative 5. I have the square root of 1 over 49. That's the same thing as the square root of 1 over the square root of 49. Square root of 1, if we go back up to our list up here, it's going to be just 1. For part D, I have the square root of the sum 9 plus 16. I'm going to go ahead and add those two together. So I get the square root of 25, and the square root of 25 is just 5. Part E looks like part D, except for the square root of 9 plus the square root of 16 are separated. They're not both under the same square root sign. So if I do this separately, 3 plus 4 is 7. Now let's look at what happens. We'll see more of this in the next section. But what if I have the square root of negative 64? Well, some students might answer the answer is 8. But does 8 squared equal negative 64? And the answer is no. Negative 8 squared would be positive 64. so that would not work also. So the answer to this problem is the square root of negative 64 is not real. It's not a real number. And the same thing is true for the square root of negative 25. So when you take the square root of a negative value, it's always going to be not real. They're not real, and we'll talk about in the next section what to do with these not real numbers. So can we graph these on the real number line? No. Everything that we've done up to this point, we can graph. We can graph the 7. 7 would be 1, 2, 3, 4, 5, 6, 7. It would be right there. That would be 7. We could graph 5. 5 would be right here. We can't graph these values here. They're not real, so they're not going to be on the real number line. Okay. Now, in example 2, what happens if we try to take the square root of something and we don't go back and we can't find it on this perfect squares list? Square root of 75, there's nothing squared that will give me 75. But if I look at 75 closely, 75 is made up of factors, and one of those factors is a perfect square on the perfect square as 3 times 25. Okay, so let's see what happens if I do that. We'll go back to this problem, and so I haven't really done anything illegal. I just rewrote it. The reason I did that is because the square root of 25 is a perfect square. Okay, so if I separate these two into 2 square roots, this right here, I'll go ahead and circle it in blue, we know what that is. The square root of 25 is just 5, so that would be 5. And we drop down the square root of 3. What I've just done there was I just simplified the square root. Okay, so square root of 75 is the exact same thing as 5 square root 3. It's just 5 square root 3 is simplified. Okay? So in part B, I have square root of 72. And again, 72 is not up here on this side of the list. I'm looking on this side right here. I don't see 72 on this side at all. Right? So what we're going to do is we're going to go ahead and look for 72 as being a product of 2 factors, and one of the factors is on this side. Okay? Oops. On this side right here. So 2 numbers that multiply give me 72, and one of them's got to be one of these in the yellow. Well, this is too big, too big, too big, too big, and so on. Too big. Now, 36. Now look at 36. 36 times 2 is 72. Okay, so let me go ahead and erase all this stuff in the yellow so we can make our list a little bit cleaner here. And so remember that 72 is the same thing as 36 times 2. Okay, equal to the square root of 36 times 2. Now I separate those. Just see how the square root 2, and now I have simplified that square root. Pretty neat. Now part C, square root of 6x times square root of 3x, 6 right here, there's no way to make 6 into a perfect square. There's 6 if I go back up here to the list, and I apologize for going back and forth to the list. But 6, I can't take anything times one of these numbers on the left hand side to get 6. Rewrite this as the square root of x gives me x squared. Because once I do that, I now get the square root of 18x squared. And now the square root of 18, isn't that the same thing as the square root of 9 times 2? And 9 is on that list, isn't it? So when I separate this, I get the square root of 9, square root of 2, and the square root of x squared. Square root of 9 is 3. Square root of x squared is x. And square root of 2 is... Sometimes students, and I like to do this too, I like to circle these, because I know that they're coming out of the radical. And when I do the square root of 9, you see how that was the third right there? Square root of x squared, and that's where the x came right there. Okay. One of the big objectives when simplifying square roots is we will always want to find the largest, or it means that we just have a little bit more work to do. So I'm going to go back to this problem that we did a second ago. We did the square root of 72, example 2. And I broke 72 up into 36 times 2. What if I did not use 36? And what if I looked at this list up here and I said, well, 72. I look at this list and I go, these are all way too big. And let's say I skipped 36. I didn't look at 36. I keep going, I go, oh, is it 9 times 8 72? That's true. So I'm going to use 9 and see what happens. So if I rewrite this as the square root of 9 times 8, I get the square. The problem is if you look at the square root of 8, 8 is made up of 4 times 2, and 4 is a perfect square. So I get, I'm going to write over here, I get 3 square root 4 times square root 2, and this right here is 2. So I get 3 times 2 square root 2, and I get 6 square root 2. Do you see I got the exact same answer as I did up here? But how many extra steps did I have? In this problem, in part B, I had 1, 2, 3 steps. When I did it down here, I had 1, 2, 3, 4, 5, 6, 7 steps. If you find the largest or the greatest perfect square factor, it shouldn't be more than 2 steps like I had in example 2b. I always tell students it's very similar to doing or reducing fractions. If I had both a numerator and denominator by 20, and you divided it by 2, you'll get 10 over 20. Divided by 2 again, you'll get 5 over 10, and divided by 5, you get 1/2. I still get the same answer, but how many extra steps did I have to do? 1, 2, 2 or 3 more steps. And if you find the largest common factor, it saves you some steps. Same idea here. If you find the greatest perfect square factor, then you have less work to do. Okay? So I always suggest looking at the correctly. Okie dokie. So let's go ahead and, now that we know how to simplify radicals, let's go ahead and do the operations on radicals. And the first example, in example 4, we're just going to go ahead and add or subtract. Now when you add radicals or subtract them, you just want to make sure that your radicand is the same. So I think of it as like 9x plus 4x. These are the same right here. They're like radicals. So what I'm going to do is I'm going to go ahead and add the coefficients 9 and part B. I have the square root of 6y minus 4 square root of 6y. These are like. And now technically I only have one of them right here. So I have 1 minus 4, which gives me 3. Actually, negative 3. And I keep that radical part, square root alike. So 6 square root 5 plus square root 20, they're not like at all. This is different than this. I can simplify. And the square root of 5 I can't simplify. There's no perfect square. Isn't the square root of 20 the same thing as the square root of 4 times 5? And I knew 4 is the perfect square, so I get the square root of 4 times the square root of 5, which is 2 square root of 5. So I can now replace this with 2 square root of 5. So now when I do that, notice how they're now like right here. So I now have 8 square root of 5. Okay. In part B, these definitely aren't alike. I have square root of 12x, and I have square root of 75x. So I can't add or subtract as as written there. So I'm going to go ahead and I'm going to look at square root of 12x, and I'm going to off to the side. I'm going to actually write this whole thing out for square root 12x. And that's the same thing as 4 square root, and 12 is made up of 4 times 3, and 4 is the perfect square, and then the x is still there. So I get 4 square root 4 square root 3 square root x. Okay, this right here is 2. So I get 4 times 2 square root 3 square root x. I get 8 square root 3x. I put that back together because square root of 3 and square root of x can't be simplified at all. So I put it back under the radical. So over here I have 8 square root 3x minus, and I'm going to go ahead and look at 2 square root 75x, same as 2 square root and 75. Again, you can go back to your list up here. 75 is made of a perfect square. These are all way too big. Way too big. Way too big. And if I stop at 25, I think 25 times 3x. I get 2 square root 25 square root 3. And I put those back together because I can't take the square root of 3 or the square root of x. I get 10 square root. These are the same. So 8 minus 10 is negative 2 square root 3x. Okay, so make sure when you're trying to add or subtract, make sure that you have the same radical parts. And if they're not, when you simplify, they may become alike. And it's not going to always be alike. So you might have some in your homework where even after you simplify them, they're not alike, then you can't combine them. Add an equivalent expression in which the denominator no longer contains any radical is called rationalizing the denominator. So what we want to do is we want to make sure that our denominator doesn't have any radicals. So I'm kind of foreshadow with these things here. Okay, if I have the square root of 6 in my denominator and I want to get rid of that radical, well, I want to go ahead and build 6 up into a perfect square. So 6, I want to build up into one of these numbers here in yellow. So one of these numbers. 6. So I want to build 6 into one of these numbers. And look, if I can do this, I can do 6 times 6 will give me 36. So this is what I'm really trying to do here. I want to end up, because the square root of 6 times square root of 6 will be the square root of 36. But if I multiply the bottom or the denominator by the square root of 6, you can't legally do that unless you multiply the numerator by the square root of 6. Because this is the same thing. So I multiply the denominator by square root of 6. Down here I do get the square root of 36. And on the numerator I get 15 square root of 6. That gives me 15 square root 6 all over 6. And if I reduce these two factors here, they both reduce by 3 or divide by 3, and I get 2 here and I get 5 there. So I get 5 square root 6 over 2. Same idea applies for part B. I want to build the square root of 8 into a perfect square factor, and that would be the square root of 64. You might notice a pattern here. If I multiply the square root of 8 by the square root of 8 times square root of 8 top and bottom by square root of 8, that will give me square root of 64, and these are the same. That will always work out if you're doing square roots. Okay, so down here I do get the square root of 64, and up here I get 12 square root 8. That gives me, I get, divided by 4, I get 2, 4, I get 3, I get 3 square root 8 over 2. Radical expressions that involve the sum and difference of the same two terms are called conjugates. Some examples of conjugates are, I'll give you a couple examples. If I have, there's a sum and difference right there, and they have the same two terms, 8 and the square root of 3. Okay, they're the conjugates. Another example of conjugates would be something like 7 minus square root of 5 and 7 plus the square root of 5. Sum and difference, and they have the same terms right here. Okay. And let's do one more. If I had 7, what happens when you multiply conjugates? And this is why, in the next example we'll see why we're doing this, but what happens if I take these two conjugates and multiply them together? Let's go ahead and do it off to the side here. 7 plus the square root of 2 times 7 minus the square root of 2. Okay. If you remember how to FOIL, we'll talk more about foiling on in the next section, maybe the section afterwards, I can't remember. We multiply the first terms. So first times first. 7 times 7 is 49. Outer times outer. So 7 times, square root 2 times 7 is positive 7 square root 2. And then last would be these two right here. Positive times the negative is negative, so minus square root of 2 squared. Okay. Look at this carefully. This would give me, these two together would add 0. Okay, so negative 7 square root 2 plus 7 square root 2 would be 0. So go ahead and drop down the 49 minus square root, something as square root of 2 times square root of 2, which is equal to square root of 4, which is just 2. So notice how the square negates the square root. I get 49 minus 2, and I get 47. So when you multiply two conjugates, you end up with no radicals in your answer. That's interesting. Rationalize the denominator of 8 over 7 plus square root of 2. Now remember, rationalizing the denominator means we're getting rid of the radical in the denominator, which is right there. So what we gotta do is we gotta get rid of this radical. How do we get rid of it? Let me go ahead and write the problem out again. I need to multiply by something to get rid of that square root of 2. How do I get rid of that? Let's kind of look back up to here. When we took this, we multiply it with this, didn't we get rid of the radical? So what we want to do is we want to go ahead and look at this denominator. We want to multiply this denominator by 7 minus the square root of 2. We can't do that unless we multiply the numerator by the same thing. That same thing is 1. Okay, so let's go ahead and do that. Distribute the 8. So I get 8 times 7, I get 56 minus 8 square root 2. Now the denominator, if I were to FOIL all this out, I've already done it here. Okay. So you can do that off to the side and you'll get 47. And on the test, what you would do is you would do this problem right here off to the side, right here. Okay. Then you get 47. So what I have here is I have 56 minus 8 square root 2 over 47. That's the answer. You can't combine these two terms because they're not like. One has a radical and one doesn't. If you want, another way to write the problem out is you could rewrite it out and write or, because you could write 56 over 47 minus 8 square root 2 over 47. Some people like to separate it out. Doesn't matter to me. Okay. On page 12, we're going to go ahead and look at simplifying. Now we're going to simplify the cube root. And the cube root is right there. If we don't have, and so now we have a cube root. That means I want to look at the perfect cubes list, and I just want to simplify this. So I'm going to go back up there. In fact, I'm not even going to go back to the list. I'm just going to go ahead and write off to the side here. 1 cubed equals 1, 2 cubed equals 8, 3 cubed equals 27, cubed equals 216. Okay? So 24. We want to make 24, and if 24 is on this side, then we have a perfect cube already. We don't. So I go up this list. This is the same thing as the cube root of 8 times 3, because 8 times 3 is 24. Now I break it up or separate it. I get the cube root of 8 times the cube root of 3. The cube root of 8 is just 2. See that? So I get 2. And the cube root of 3, I can't break 3 up into one of these on the left-hand side. And the cube root of 3 is not perfect, so I just leave it as the cube root of 3. And there's my answer. Okay, now part B is interesting because here I have the fourth root, and I've never made a fourth root list, perfect fourth root list, and I would expect you to memorize it, but you can always make one up. 1 to the 4th power is 1, 2 to the 4th power is 2 raised to the 4th power, which is 16, it's 81, 4 to the 4th power is 256, and etc. Now 8 cannot be broken up into one of these numbers here. Same thing with 4. So I can't even simplify those separately. But what I can do is I can go back to what I did before, and I can go ahead and combine these and get the fourth root of 8 times 4, which is 32. Now once I do that, now I look at this list again here, and I go 32. Can 32 be broken up into two numbers? One of them be on this side. And there it is. So it's the fourth root of 16 times 2, which is the fourth root of 16 times the fourth root of 2. And the fourth root of 16 is going to be just 2. I get 2 and then the fourth root of 2. Maybe fractional. And we see a lot of this later on in the course. So I'll try to remind you guys one more time about rational or fractional exponents. It comes really late in the course, so hopefully you'll still remember the definition of rational or fractional exponent. Okay, so I'm going to go ahead and give you the definition. And if I have something, some base, and the x, okay, what that means is I have this bottom number, this denominator of the fraction exponent. That's going to be your index of your radical. So that would be the root. This number on top or in the numerator is going to be your power. That goes outside here, and that's your power. Okay. So if I have, in example 10, 64 to the 1/2 power. So what is your index? So it's going to be out here. And again, we do the square root. We don't really normally write that 2 out there, so I'm going to erase that 2. But it's understood to be 2. And that 1 up here means I have power of 1. Well, inside here, square root of 64 is just 8. 8 to the first power is 8. So this is equal to just 8. Okay, in part B, this 3 means I have the cube root of 125, and the 1 means I have a power of 1. The cube root of 125 is just 5. By the first power, and I get 5. My answer is going to be negative. The 1/4 exponent only applied to the 16. Okay, so the fourth root of 6. Well, this is going to be fourth root of, so I get 2, and 2 the first power, 2, and then drop down the negative sign, that's negative 2. Now part D, notice how this negative sign is inside the parentheses, that's part of my base. This one was not in parentheses, so it's just got dropped down in the answer. So here I have the cube root of negative 27. This is the index that goes out here. And right to the first power. The cube root of negative 27 is negative 3. How do we know that? Because negative 3 times negative 3 times negative 3 is negative 27. This is positive 9 times negative 3 is negative 27. To the first power, which gives me negative 3. Okay. Now part E. Part E is going to take something that we learned in the previous section and bring it down to this section and add something else to it. 64 raised to the negative 1/3 power. I have a negative exponent. Okay. Do you remember what negative exponents mean? It means that we have to move the base position. It doesn't mean we have a negative answer. What this means is that I can remember the definition of a negative exponent. So I have now 1 over the cube root of 64 raised to the first power. And the cube root of 64, if I look at this carefully, is going to be 4 with all the denominator. So I get 1 over 4. If you can do that problem, then you've actually taken something that we've done in the previous section and you did this section. Cool. Okay, example 11. I'm going to do the same thing. I'm going to go ahead and use my definition of fractional exponents. This 3 means I have a cube root of 27. And this 2 means I have a power of 2 on the outside. So if I just look inside here, the cube root of 27 is 3. Get a different color there. And then I square that and I get 9. So my answer is 9. In part B, this 2 down here means I have the square root of 9. Again, there's a 2 understood to be out here, but I don't write it because if we don't write it out there, we know the 2. I have a power of 3 on the outside. So this right here is going to be 3. I drop down the exponent of 3. So I get 27. And part C is just like the last part in the last example. I have a negative exponent. So remember, negative exponent only indicate position. So now I'm going to take this 81, move to the denominator, and then by doing that, my exponent becomes positive. Okay. Now I have the 4th root of 81 to the 3rd power. The 4th root of 81, don't know that, but luckily I wrote the list right here. The 4th root of 81 is 30. Okay. In the last example, I want you to simplify the 9th root of x to the 3rd power. Okay. So if you look at this carefully, you have the 9 on the outside of your index, and then 3 is your exponent. This is the same thing as x, and then this is your index. This is going to be your denominator. This 3 is your exponent, so it's going to be out here. So I get x to the 3/9. And like any fraction we dealt with before, if we can reduce that fraction, we will. 3 over 9, same thing as 1/3. And then if I want to go ahead and rewrite it back into the format I had in the beginning, which is this, then that would be the same thing as the cube root of x, and that would be the 1st power. And again, that 1's not really necessary, so it would be the cube root of x. And you can put the 1 there if you want to also, but again, that's not necessary either. There's your answer. Okay, that's the end of P3. And out there, remember on your exam, when you get your exam packet, I would go ahead and just write it on the exam packet as soon as you get it so you have it in front of you to work with. Okay?